Hello, here's a few capacitor questions. We're starting here with a charge capacitor connected across the ends of a negative temperature coefficient thermistor kept at fixed temperature. Right, so negative temperature coefficient means as temperature goes up, resistance goes down. Capacitor discharges through the thermistor. The potential difference V across the capacitor is a maximum at time t equals 0. On the axes below, carefully sketch a graph to show how potential difference V across the capacitor varies with time t. Label this graph L. Right, okay, so we want to try and indicate that we're getting this 1 over E exponential decay on this, how capacitors discharge, whether we're doing the potential difference or the charge stored or the current, they're all decaying in the same way. Now, we haven't got any actual values to deal with here, but we can, what is this, 6 high. So if we start here, by the time we've taken one time period, so one time constant, so let's say we've gone to here is a time constant. So let's say we've got a few time constants going along here. So we need to have dropped to about 37% of this. So down to say, I don't know, maybe here, something like that. And then, so we've got V0 at the start. Then we've got V0 over E is going to be here. And then we're going to have V0 over E squared will be here. So you can at least mark on something like that to show that you know how this is dropping off in an exponential fashion, and then join up the dots in a smoother curve than I'm managing here, but an exponential decay. So yeah, if we've got this as our, well, you could mark that as t, 2t, 3t, and then maybe even say t is equal to the time constant. So, I mean, that may be way over the top for what they actually want, but it does say here, carefully sketch a graph. And I think just drawing in an exponential decay might be a bit, you might be losing a mark there. So for the sake of putting on a couple of little values there for L, label this graph L, you're going to pick up marks by putting those labels on. Temperature of the thermistor is increased to a higher fixed value, right? So its resistance would have dropped. On figure 4.1, sketch another graph to show the variation of V with T when the same charged capacitor is discharged across the ends of the hotter thermistor. Right, so if we've got a lower resistance, so higher temperature, lower resistance, smaller time constant, quicker discharge, so we're going to have the same sort of shape, but it's going to come down steeper. So that's what we want. So it's going to be below the red line all the way along. It's really hard to draw on this screen, but that's our H. So we've got one graph which is dropping off fairly quickly like that. The original one was dropping off more like this. So we've got same shape of curve, but with a higher temperature, it discharges quicker. Explain how you can show that the graph sketched in I as a constant ratio property, i.e. exponential decay. All right, well, this is what I was getting at with these labels here on the y-axis. So we're saying that we've got a constant ratio, because I mean, I've mentioned that here, of V values. I mean, they've called the potential difference V, so we can use that in our answer. Constant ratio of V values for fixed time intervals. Fixed time intervals. This is exactly what I was marking on here. Every time we're going up by t, every time we're going up by this time constant, we're getting another factor of 1 over E thrown in. So these ratios are going to be constant. Right, on to the next bit of the question. We've now got an electrical circuit. Okay, so we've got a couple of capacitors, we've got our cell, we've got a fixed resistor, an ammeter, and then this vibrating switch. 1.4 volt EMF. That's in the diagram, so we don't need that. Negligible internal resistance, okay, whatever. Values of the capacitors on there. Right, 120 hertz is the thing that I haven't marked on here for the speed of vibration here of the switch. Calculate the time constant of the circuit. Okay, so the time constant is equal to the capacitance multiplied by the resistance that is discharging through. So our capacitance is, well, these are in parallel, so we're just adding them up. So that's 6.9 times 10 to the minus 6 multiplied by 240. So I'll just whack that in the calculator. I think it's going to be the way to go. Oh, actually, it's quite an easy number though, isn't it? But no, I'll stick with the calculator. So 1.6, I've already started typing it in now. 656 times 10 to the minus 3, which is 1.7 times 10 to the minus 3 seconds to two significant figures. Okay, calculate the value of the average current I in the resistor. Assume that the capacitors are fully discharged between each throw of the switch. Right, okay, so average current, we need to get the amount of charge then that's on the capacitor, because we've got two ways of working out charge. We've got our Q equals CV for the capacitor, but that's also equal to IT for the current that's flowing. So we can equate CV and IT, and we can use that to work out what I is. So we've got the current is going to be the capacitance, which is our 6.9 times 10 to the minus 6. Then we've got our voltage that we use to charge up the capacitors, which is the 1.4, because that would have been the PD that we had across them when they were fully charged. Then we need to divide by the time. Well, the time is 1 over the frequency, so we're dividing by 1 over 120, so we are just going to be multiplying by 120 on all of this. So we're going to have, yeah, just multiply the numerator by 120, gives us what we got, 1.1592 times 10 to the minus 3, which is 1.2 times 10 to the minus 3 amps. Again, to two significant figures. The frequency of vibration of the mechanical switch is doubled. Explain why the average current in the circuit is not doubled. Right, so if we've gone to 240 hertz, then that means, well, how long are we going to have to discharge? That means that our discharge time is going to be equal to 1 over 240, which is 4.2 times 10 to the minus 3 seconds. Now, that's not a million miles away from our time constant. I mean, that's less than 3 time constants. Less than 3 time constants. So, I mean, at least before we had sort of 5 time constants, something like that, you're going to get a long way down our discharge curve. If you've got 5 time constants, less than 3 time constants, we can say that the capacitor's not fully discharged. Capacitor's not fully discharging. Cool. Right, so that is, I think that's the end of the question. Yep, it is. We're on to the next one. Right, so define the time constant of a capacitor resistor discharge circuit. The time constant is equal, well, yeah, for that. So that's equal to the time taken. I was just wondering whether to contextualize, but it's just repeating what they've said in the question. The time constant of a capacitor resistor discharge circuit is equal to the time taken for then we could say the potential difference or the current or the charge stored to decrease to 1 over E times the initial value. All right. Part B. Student designs a circuit with time constant 5 seconds. State suitable values for resistance and capacitance. Right, well, you can pick anything that multiplies to be 5 here, but let's not pick crazy things. I mean, they've actually got a 0.01 sitting here. suggesting a sensible value of capacitance. So why not go with that then? So we could say that 5 is equal to 0.01 multiplied by, so we've got to go on that to 500. That would come out what we want. So we could say, therefore, we could have C is equal to 0.01 farads, R is equal to 500 ohms, and we're just using the value that they've got here in part C. So, why not? Right, now they've given us this circuit, couple of switches, type bundle of wire, 12 volts. Right, they've given us some details on the wire. Diameter, and resistivity, right, okay. Density, specific heat capacity, right, they've given us loads of stuff on the wire. Calculate the time constant of the circuit. Right, well, we're going to need the resistance then of this bundle of wire because we don't have that yet. So the resistance is the resistivity multiplied by the length divided by the cross-sectional area. So 4.9 times 10 to the minus 7 multiplied by 5 divided by, all right, we need cross-sectional area, right, 6 times 10 to the minus, what would that be, 5 squared, that's our r squared, multiplied by pi. So let's just simplify it a little bit before typing all this into the calculator. What we're going to have 24.5 over 36 pi times 10 to the 3. Right, now I will be going to the calculator with all of that. To 16.63, which is 220 ohms to 2 significant figures. Right, that was good. Quite a lot of calculating to do, but there you go, all easy stuff. Switch S2 is open, switch S1 is closed. Explain in terms of the movement of electrons how X and Y acquire equal but opposite charge. Right, so we want to say that electrons are removed from, which way are we going? So conventional current is that way, so we're going off of X. Electrons removed from X, which means it becomes positive. And then we can say, and electrons added or deposited to Y, which means it becomes negative. But then we can say also that the same current onto Y off X means that we're going to get the same charge, equal charge on X and Y, equal and opposite charge on X and Y, equal and opposite charge on X and Y. So again, obviously turn those into proper sentences, but we're saying how we're getting electrons onto one plate, off of the other plate, and why they're going to end up being the same. So that's good. Switch 1 is opened, right, so it's charged up. Potential difference across the capacitor is 12 volts, right? So yeah, we're fully charged up there. Everything's good to go. Switch S2 is now closed. Assume that all of the energy stored by the capacitor is used to heat up the bundle of wire. Calculate the increase. Right, so our energy on this, well, we've got a half CV squared. That's what we've got stored on the capacitor. And that's going to be equal to our M, specific heat capacity. Right, we don't want to get our C's mixed up. So let's call that a big C for the capacitance and then a little c here, MC delta T. So that means that our change in temperature is going to be, well, we got a half multiplied by the capacitance is 0.01 multiplied by square of the voltage, so 144, divided by, then we've got, we've got to work out what M is. How annoying. Right, C is 420. C is 420, that's fine. And then our, we've got to work out this mass. So we've got the density times the volume. So density is 8,900 multiplied now by the volume. So the length is 5, and then we need our pi r squared again. So a pi and then 6 times 10 to the minus 5 squared. Right, what a mess that is. Not to deal with, but we're just going to be whapping this into the calculator. Quite a lot to type in. It's taking blinking ages, this is. But it comes out at 3.4 Kelvin or degrees C, whichever one you want to go for. Doesn't really matter. Right, so yeah, again, it's just making sure you don't make a calculator mistake really on that one. State and explain how your answer to that last part of the question would change when a 24-volt power supply is used to carry out that experiment. Right, so if the well, I'll have to go up here, but we're doing one of these chains, so voltage times 2, therefore energy times 4, therefore delta T times 4. So the temperature is going to go up 4 times the amount, so 4 times 3.4. Okay, that was yeah, that was fine. That question, not particularly exciting, but it was all right. Bit fiddly, I suppose. Right, last one in this block. There's an arrangement of capacitors. Determine the total capacitance. Right, so we're going to have to get the two in series first and then just add on the 500 at the end. So common denominator, this is like adding up resistors in parallel. So we'd have 1 over 300 and 3 over 300. So 300 divided by 4 is 75 microfarads, and then we add on the 500. So 575 microfarads. Part B, a capacitor of capacitance 500 microfarads charged to 6 volts. Student places a thumb and first finger across the terminals of the capacitor as shown in figure 1.2. Okay. Provides a high resistance path for the capacitor to discharge. Use figure 1.3. Okay, so the graph. Oh, right, this graph. There's a little caption here. This is the variation of potential difference across the capacitor with time. Right, okay. So use this to calculate the resistance across the terminals of the capacitor. So the resistance of this girl stuck her fingers on the end of these. Right, so we need to get our time constant. So when we're dropping down to 1 over E, so our CR, our time constant, is equal to, well, if we're at 6 and we want to be just over a third, so we want to be just above 2. So let's say here, 60 seconds. 60 seconds, and we got they told us capacitance somewhere, didn't they? Yeah, here we go. 500 microfarads. So our resistance is 60 divided by 500, and then we're going to be multiplying by 10 to the 6 because we've got that micro that we're dividing by. So that's going to be, get rid of those, we'll have, that'll be 10 to the 5 rather than 10 to the 6, and we'll have 6/5 is 1.2. So 1.2 times 10 to the 5 ohms. Excellent. Calculate the energy lost by the capacitor from time t equals 0 to t equals 30. Right, so our energy is equal to a half CV squared, because we're all dealing with voltages and capacitances here. So our change in energy is going to be a half C times our V0 squared minus our new V squared, because we're just subtracting one from the other. So that is 5 times 10 to the minus 4 divided by 2. So we're starting at 6 volts, so 36. Take away, where are we after? So after 30 seconds, which is what here, we are at 3.6 squared. So again, I'll just go to the calculator on this one. This is 5.76 times 10 to the minus 3, which is equal to 5.8 times 10 to the minus 3 joules. That's a fairly straightforward one at the end, but that was quite nice. I suppose we did have to do this bit with the time constant. So again, it's worth being able to match time constants to graphs and being able to read those off nicely, because that can be something that's quite easy to miss, I think, in this question. There you go. Right, that's another block. I've got another set of capacitor questions coming up.